When we are dealing with vertical movement, this is known as free fall. In order to be in free fall, an object only experiences acceleration due to gravity. Recall that the acceleration due to gravity on Earth's surface is going to be 9.8 meters per second squared. Please bear in mind that as you go further away from Earth's surface, technically the value of gravity becomes less and less until you get out into space. Let's talk about now our focus being on vertical motion. A tennis player on serve tosses a ball straight up into the air. So just for our purposes, I'm not going to draw it straight up. I'm going to kind of draw it at an angle, but please keep in mind that we're not doing angles in this class. Okay, so I'm going to draw this a little differently. You know, it should be going straight up and straight down. That's horrible. But what I'm going to do instead is I'm going to draw it like this so that we have some, so we can see what's going on. No angles here. If I throw something straight up, it would come straight down. Now, a few points that I want to bring up. We have the initial, we have the final, and then we have this point up here, which we're going to call the apex.
Perfect.
This is a parabola, and so you'll be encountering these possibly next semester in Algebra 1. For sure, you'll talk about these in Algebra 2. So this will be the maximum height at which the object, the ball in this case is being thrown straight up, will hit before it comes right back down. All right. Let's talk about the acceleration. Now, when you launch this ball, you'll notice that the ball starts to slow down until it gets to this high point right here, and then it speeds up on the way back down. What is responsible for the slowdown and the speed up is going to be gravity. Okay, so acceleration in this point, in this problem, is going to be completely gravity, meaning that this is actually a free fall problem. And in this case, the gravity will always be pointing downward, always. So gravity is pushing down at at the beginning, gravity is pushing down at the top, gravity is pushing down at the end. Gravity is always pushing down, and gravity is constant. It's going to be at 9.8 meters per second squared. So regardless of where you are in this whole trajectory, right? Trajectory is the path that an object takes as it flies through the air. Throughout the whole trajectory of this tennis ball, the acceleration will only be gravity because it's a simple ball. Only objects that have rocket engines or repulsors or impulse or anything extra, any object that can change its velocity would have a different acceleration. If the object has no capability to change its velocity, then it's completely free fall and gravity works on it at all times. What about the velocity? This is interesting because if I launch this thing with a velocity, an initial velocity, as this goes further up, the velocity gets smaller and smaller and smaller until at this point right here at the apex, the velocity is 0 at the apex. Think about it. You throw something up in the air, and then it goes ahead and for a split second, it stops in the middle of the air. It changes direction, okay? And then at that point, it starts to accelerate downward. As it accelerates downward, it starts to pick up speed. What is causing it to accelerate downward? It's gravity, as we discussed in part A. Okay, this is the final velocity. But you'll notice that the velocity actually changes because gravity is affecting it. At first, you have a high velocity going upward, you'll notice. Gravity is going downward. And so the velocity is going upward. This is opposing, right? We talk about this Newton's laws with free body diagrams. You have a positive and a negative end. So in one, you have the velocity going up in one direction. It's 0 at the apex, and then it changes direction and it goes down. So at the apex, we notice that the velocity is 0, right? That's at the maximum height.
Most impressive.
You'll also notice something interesting, that the initial velocity is actually equal to the final velocity. So I propose to you that the speed at which, or the velocity at which this tennis ball was thrown upward, will be the same velocity at which it's caught, except it's at an opposite direction. So one might be positive and the other one might be negative. Okay? Based on this situation that I have right here where I've drawn it, if I'm looking at this left side, I would consider gravity to be positive, and I would consider velocity to be negative because it's going in the opposite direction.
Oh yeah.
If I were instead looking at this side, I would have gravity be positive because it's going downward, and I'd have velocity to be positive as well. So it changes depending on which side you're on.
Perfect.
How do the kinematic equations change? Well, you'll notice that these are the ones we've been using for a while. This is for the x-axis, left and right horizontal motion. And what changes is that all your accelerations become gravity when it's free fall, and all your displacements on the x-axis become displacements on the y-axis. You'll notice those subtle changes, but other than that, we're looking pretty good. The only difference you must be aware of and attentive to is positives and negatives. Be careful with that. Gravity will be going down, but the object might be going up. So keep track of that. We'll do a problem eventually with that information. Here's a golf ball that's being released. For some reason, students find this problem extremely informative to their intuition and their conceptual learning of free fall and motion. We have a golf ball that's released from rest. So it was just dropped. Okay. We're not telling you how tall this building is, it's just very tall. So let's see what happens at the 1 second, 2 second, and 3 seconds. And I want to suggest you add 4 seconds row and also add a velocity column. Okay. Now we've used kinematics to go ahead and calculate these numbers, but look at what happens. You have 1, 2, 3, 4. Notice what's happening with the velocity. It's going up by 9.8 each time. No big deal. We're not multiplying 9.8, we're just adding 9.8 each time. But look at the displacement. It's actually getting bigger and bigger each time. This time it looked like about 15, right? This time it looked more than that, and it keeps going and growing and growing. Be aware of what's going on here. Let me show you an example of this. If we expand upon the data in that table of problem 3, the data table of problem 3, we'll get this graph. And you'll notice that on the x-axis it's time. As time's going by, we have two things that are being affected, velocity and displacement. Now you'll notice the velocity is linear, meaning it forms a line. Okay, you wouldn't be surprised to find out that the slope of this graph would be 9.8. And actually, the equation for this graph would be v is v naught plus g times t, or in other words, v is equal to 9.8 times t plus v naught. So you'll see that slope-intercept form right here, where this forms a slope, and this is the x, like we said before. So this is actually the first kinematic is forming this red one. You'll notice that for the displacement, this is not a line, it's actually curving. And so what we have here is what we call a quadratic. You'll learn a lot more about that, like I mentioned, in second semester Algebra 1. However, you'll guess the formula for this is delta y is v naught t plus 1/2 g t squared. And so you'll see that squared term right here is making this thing curve. And as a result of that, it's actually making this climb really fast. So what you'll notice is that if you were to drop something on accident, it's easier to get a hold of it. So let's say you're over a bridge and you drop a camera or your phone. If you catch it, if you do your best to catch it really quickly, you have a chance because it hasn't fallen far. But if you decide to catch it 3 seconds later, you're already 50 meters away. Okay. If you decide, 6 seconds later, then you're already talking about 175 meters away. And the more time you decide to think to get your phone or your camera, it's already way too late. Okay. So whereas with velocity, as time goes by, it's pretty consistent. You can expect it to go up by 9.8 each time. The displacement actually grows a lot faster. Okay. Take a second to reflect and to summarize. How does gravity really affect an object's velocity and displacement as time goes by? So in other words, take what you've learned from the graph and from this data table and try to explain it conceptually with words. Explain how the velocity climbs up, how the displacement climbs up, how they compare to each other, what happens as more time goes by.
That's all there is to it.